Hello, today we're continuing in our A-level physics revision series looking at fluid dynamics and leading up to Archimedes' principle. There's probably going to be more in this video than some of you will need at A-level, but I hope it will give you a good background. In a fluid, the pressure varies with depth, and all the points at the same height in a fluid have the same pressure. So if this is a fluid, then the pressure will increase as the depth increases, but all points at the same depth or the same height will have the same pressure. Let's first consider atmospheric pressure. Pressure is defined as the force divided by the area over which that force is applied. So let's consider the surface of the Earth, and the atmosphere goes up to a certain point, and we'll say that the height of the atmosphere is h. And what we're going to do is to consider a cylinder of the atmosphere where the cross-sectional area here is A, and the height of the cylinder is obviously the height of the atmosphere h. And we can say that the pressure, which is a result of all the air bearing down on the surface of the Earth, the pressure at, as it were, the surface of the Earth is equal to, the pressure is equal to the force divided by the area. The force is the weight of air. Remember, there's a difference between weight and mass. Weight is mass times acceleration, which in the case of the Earth's atmosphere will be g for gravity. So the pressure is the mass of the air in this cylinder times g divided by the cross-sectional area A. But what is the mass of air? Well, mass can be deduced if you know what the density is. Density is mass divided by volume. And so mass is density times volume. So mass is density, rho, of air times the volume of air times g divided by A. But what is the volume of this cylinder? Well, the volume of the cylinder is simply the area times the height. So AH. And so the pressure is equal to rho times AH, which is the volume, times g divided by A, and the A's cancel, and that gives you rho hg. So the pressure of this cylinder of air as it lands on the Earth is equal to the density of air, rho, times h, the height of the atmosphere, times g. Now this, I have to say, is only an approximation for two reasons. Firstly, the density of the air will vary as you go up in the atmosphere. It becomes less dense. And secondly, g itself will vary over the height of the atmosphere. So this is a very rough equation for atmospheric pressure. But when I was at school, the atmospheric pressure on the surface of the Earth was said to be approximately 14 pounds per square inch. These days, of course, we use SI units, and that is the equivalent of 10 to the 5th pascals, which is the same as newtons per metre squared. If pressure is force over area, then force is measured in newtons, area is measured in metres squared, so newtons per metre squared is a measure of pressure, but we actually use pascals. So this pressure is the pressure which results from air having a height h. The same pressure for water instead of air would result in h equaling 32 feet. And that's for water, H2O. And for mercury, that pressure would result from only 76 centimetres of mercury would give you this pressure. Let's now calculate the pressure underwater. So here is a fluid. It could be any fluid, but we'll call it water for the time being. We know that on the surface of the water, atmospheric pressure, we'll call that PA, is applying. But what about a point here, underwater? Well, once again, I'm going to draw a cylinder. And once again, we can say that the pressure of the water, forget for the moment atmospheric pressure, but the pressure of water on this point here, the pressure of the water is equal, once again, force over area. And once again, that force is the weight of the water in this cylinder. So it's the mass of the water times G, the gravitational force, divided by A. But what is the mass? Well, as before, we can say that the mass is the density of water multiplied by the volume of water. So the pressure is equal to the density of water times the volume of water times G divided by A. And what is the volume? Well, the volume is going to be, if we say that the depth of water is H and this cross-sectional area is A, then we can say that the volume is AH times G divided by A, and once again A's cancel out and you end up with the pressure of the water at a depth H is equal to the density of water, or the fluid, whatever it happens to be, times H, the depth, times G. And therefore the total pressure at this point underwater is going to be the combination of the atmospheric pressure plus the pressure of the water. So it's going to be the pressure of the atmosphere plus the pressure of the water, which means it's the pressure of the atmosphere plus the density of the water times the depth times G. And thus you can see that the pressure is going to vary according to the depth that you are underwater. Now the pressure in a fluid, let's take a tank of fluid here. The pressure at any given point will apply in all directions. It doesn't only apply in one particular direction. So let's take a rather large test tube. Let's make it about 1 meter long, and let's fill it with mercury. Let's say that this fluid is mercury, and we put the test tube upside down in this container of mercury, and this test tube is completely full of mercury, completely full to the top. What will happen? Well, we've got atmospheric pressure bearing down on the surface of the fluid, and that atmospheric pressure is transmitted through the fluid and is also pushing up here. And you'll remember that we said earlier that the atmospheric pressure was the equivalent of 76 centimetres of mercury. And so what you find is that the full tube, let's say this is 1 meter high, this tube of mercury, the mercury will run out until it is 76 centimetres from the surface. And it will then stay there. And that 76 centimetres of mercury is being supported by the atmospheric pressure that's bearing down on the surface and being transmitted through the liquid and is supporting this 76 centimetres of fluid. And of course, whenever atmospheric pressure changes, so the height of the mercury will also change. And that, of course, is a barometer. And a barometer can be weather dependent. If you have high pressure, then the mercury will go further up the tube. If you have low pressure, then mercury will come down the tube. That's exactly what a barometer tells you. You can use the principles of fluid dynamics to calculate the density of an unknown fluid. Let's take a system that looks like this. We have a container, and we fill it with a fluid whose density we know. Let's say it's water. Well, the water will lie in such a way that the height in both of these arms will be the same. Now we introduce a new liquid into this section here. It has to be a liquid that has a lower density than the fluid that we've got here. Let's say it's oil. And what will happen is the oil will sit on the surface, but it will bear down on the water, pushing it down and thus pushing it up on that side. And so you now have some oil here, and the rest of this is water. And what we're going to do is to measure from the height at which the oil and the water meet. And so on this side we've got H2, and that is the height of the oil. On this side, taking that across here, we've got the height H1, and that is the height of water above this level where the oil and the water meet. Now, I said earlier that the pressure at the same depth will be the same. So the pressure at that point and the pressure at that point have to be the same. But what is the pressure at these two respective points? Well, at this point, it is the pressure of the atmosphere, because there will be an atmospheric pressure bearing down, plus the density of water times G times the height of the water, which is H1. We've calculated that before. And that has to equal the pressure on this side, on this point, which is going to be atmospheric pressure, again, bearing down here, plus rho of the oil times G times the height of the oil, H2. And we know everything in this equation. That should be a plus sign there. We know everything in this equation. The rho A's, the pressure of the atmosphere cancels out. So you then simply have that rho W G H1 equals rho oil G H2. The G's, of course, also cancel. And so you get that the density of water times the height of the water, which you measure, is equal to the density of the oil, which you don't know, times the height of the oil, which you do. The only thing you don't know in that equation is the density of the oil, and therefore you can calculate it. We can use a system such as this for what's called hydraulic power, and it works something like this. You have a container where one arm is very much thinner than the other arm, and you put some kind of fluid in it. Could be water, although it's usually some kind of oil is used for these sorts of things. And of course, the oil will always come to the same height on both sides. Now, let's suppose that the area of this side is A2 and the area of this side is A1. And what we're going to do is we're going to put a force on here. We're going to press down with a force F2. And if we push down, then that pressure that will result, the pressure of course is force over area, so that's F2 over A2. So there will be a pressure, and that will push this fluid and will result in this fluid moving upwards. And there will be a force if you put, for example, some kind of platform here. That platform will be pushed up with a force, and we'll call that F1. Now, what do we know about pressure? Pressure is transmitted through the fluid. So the pressure that is applied here will be the same pressure that is applied here. So if we call this pressure P2 and this pressure over here P1, P2 is equal to P1. The same pressure applies here. But P2 is force divided by area, that force divided by that area. And P1 is this force divided by this area. And so now we have that F1, which is the force that is pushing this platform here up, is equal to F2 times A1 over A2. And what you can see from that is that since A1 is much larger than A2, that the force that you will get pushing up is much greater than F2, because F2 is multiplied by A1 over A2. A1 over A2 is a number much bigger than 1, because A1 is much bigger than A2, so you get a much bigger force pushing up. What that means is that you could put, say, a car on this area here, and you could push down and essentially push the car upwards. So even though you couldn't possibly lift a car, you can, using this apparatus, push down on the piston here, and that would push a car up here. Now that sounds as though you're getting something for nothing, and that can't be right. And the price that you pay is that you have to push this piston down a long way in order for the car to be moved up a short distance. The issue is that the work that you do in is equal to the work that is done out. Work in equals work out. And the work in is, of course, always force times distance. So if we take the force in of F2 and we push this piston down a distance D2, then the work in is going to be force 2 times distance 2, and that will equal the force 1 times the distance that you go up, D1. And that is equal to F1 D1. Now, if F1 is much larger than F2, then D2 has to be much larger than D1. And that means you have to push this down a long, long way in order to get that to go up a very short distance. So the work done in pushing down is equal to the work done in pushing up. But you pay the price in that you have to push that down a long way just to get a very small increase in height on this side of the apparatus. And that brings us to Archimedes' principle. Archimedes lived in Greek times, and so the story has it, some gold was given to a jeweller to convert into a crown. Let's say that the jeweller was given a kilogram of gold. When he came back with the crown duly weighed 1 kilogram, but the suspicion was that the jeweller had taken half the gold away and replaced it with something like lead. So you still had a kilogram of gold and lead combined, but how did you know that some of the gold had been taken away? It was Archimedes who sussed out how you could check it. And he was reported to have said Eureka as he sat in his bath. So let's see how it works. If you take a mass, let's call it M, and you weigh it using a spring balance, which uses the principle of Hooke's law, which I've covered in another video, you will find that the weight, of course, is equal to the mass times the gravitational attraction. Mass is always constant, but weight varies according to the gravitational attraction. You would weigh much less on the moon, not because your mass changes, but because the gravity on the moon is much less. Now let's take this selfsame mass on the spring balance, measuring its weight, but this time we're going to immerse it in a fluid. And when you measure the weight, you will find that it will be, let's call it W2, it will be less than W1. In other words, this mass appears to lose weight. Well, what's changed? Well, the mass can't possibly have changed, and gravity hasn't changed. So M and G are still the same, but we've lost weight, so somehow we've lost something, and we'll call it U. And U is the upthrust. U is essentially the force of the water that is pushing the mass upwards. So you've got a force mg acting downwards, but you've got a smaller force called an upthrust, which is the water that is pushing upwards on the mass. And that's why the weight of the mass in the fluid is less than the weight of the mass in air. And now we need to calculate what is this upthrust. So let's take a cylindrical object, simply because it makes the maths a bit easier, and we're going to wholly immerse it in a fluid. That could be water. And the cross-sectional area is A, and the top of the object is at a height h1 below the surface, and the bottom of the object is at a height h2 below the surface, or a depth, if you like, below the surface. And we know that pressure increases as you go down. So the pressure, which we'll call pressure 2, at that point is going to be much greater than the pressure at that point, because pressure increases with depth. We've shown that. P2 is greater than P1. And we're going to call the difference in pressure, delta P, P2 minus P1. So the difference we're going to call delta P. Now earlier we showed that the pressure at any point in a fluid, at any depth, is equal to the atmospheric pressure plus the height, or the depth, times the density times G. And using that we can say that the pressure at P1 is going to be the atmospheric pressure plus H1 times rho G, and the pressure at P2, that's here, is going to be the atmospheric pressure plus H2 rho G. And the difference in pressure, delta P, which of course we defined as P2 minus P1 up here, is going to be equal rho G into H2 minus H1. And we're going to call that the difference in height, which is this distance here. We're going to call that delta H. So this is rho G delta H. Now let's just remind ourselves that pressure is defined as force over area, and therefore force is equal to pressure times area. And therefore if we take this delta P here, we can say that the difference in the force between these 2 points is equal to the difference in the pressure times the cross-sectional area, using this formula here. And that's going to be equal to rho G delta H, which is essentially delta P, times A. And that difference in force is the upthrust. It's the difference between the force at that point and the force at that point. The force at this point is greater, pushing upwards. And so you've got what is called the upthrust. And that's what it is. But we can simplify this a little bit more, because we can look and say that A delta H, A times delta H, is the volume of this cylinder. So A delta H is the volume, and the volume times rho, remember this is the density of the water, that gives you the equivalent amount of, the equivalent mass of water that has been displaced by this cylinder here. When you put this cylinder in the fluid, the equivalent volume of fluid has to be displaced to make room for it. And that's that volume there. If you multiply that volume by this, the density of the fluid, in this case water, then you get the equivalent mass of that volume of water. And so this now simply becomes the mass of the water displaced times G. And so you now say that the upthrust is simply the mass of water displaced times the gravitational force. And that is known as the upthrust. Now, a floating body displaces its own weight of fluid. And we can see why that should be by looking at a tank where there is some fluid in which we have a floating body. Now, a floating body will be one where part of it is under the fluid and part of it is above the fluid. The total mass of the object, let's say, is mass m, and therefore the force acting downwards, or the weight of the object, is mg. The total mass of the whole object multiplied by g is the force acting downwards. But there's also an upthrust which is equal to the weight of fluid displaced. And if that upthrust, which is acting upwards, is equal to the force acting downwards, mg, then the net force is 0 and the object will simply float because there's no force acting to make it either go down or up. And in those circumstances, the force acting downwards, mg, equals the force acting upwards, which is the upthrust, and that's the condition for the object to float. But we know that the upthrust is the weight of the fluid displaced. And that equals the volume of the fluid displaced, which is just the volume of the bit below the surface of the water. So we'll call that the volume of what's below the surface, times the density of the water. That gives you the mass of the water, times g is the weight of the water. And that is equal to the upthrust. Remember, the upthrust is the weight of fluid displaced. The weight is equal to the volume times the density multiplied by g. And obviously those two terms are equal because they both equal u. So you have that mg is equal to the volume that is underwater times the density of the water times g. The g's cancel and you get that the mass of the object, the total mass of the object, is equal to the volume of the part of the object that's underwater times the density of water. That should be a little arrow there. Mass of the object is equal to the volume of water displaced times the density of that water, but that of course is just equal to the mass of the water displaced. And so we deduce that for a floating object, its mass is equal to the mass of the fluid that has been displaced. And that's a necessary condition for the object to float. So let's consider something like an iceberg floating in the sea. Here is the sea. Here is the iceberg. It will have an irregular shape, but let's just put it in the water like this. And we can say, as we've just shown, that the total weight of the iceberg, where the total mass of the iceberg is m, is going to equal the volume of the water displaced, which is essentially the volume underwater, times the density of the water. So this is the total mass of the iceberg times gravity is equal to the volume of the seawater that has been displaced, that's just the part that's under the water, times the density of the water. Times g, of course. And since the g's cancel, you've got that the mass of the iceberg is equal to the volume of water displaced times its density, which means that is the mass of the seawater displaced. Now v is the volume that is underwater, but let's consider the total volume of ice. That's all of it, above and below the water. Then what we can say is that the mass, this mass of ice, is equal to the total volume times the density of ice. Okay? And that, of course, is going to equal, because mass is equal to the volume underwater times the density of water, that equals volume times density of water. And thus we get the equation that V divided by, that's the amount underwater, divided by VT, which is the total volume, is equal to the density of ice divided by the density of water. And since the volume underwater is less than the total volume, this is less than this, that means that must be less than that. So the density of ice must be less than the density of water, and that's why ice floats on the water. Now, in the case of an iceberg, or indeed any floating object, what is the proportion of the volume of the object that is underwater? Well, you can deduce that if you know the respective densities. Now, in the case of ice, the density of ice is approximately 0.9 grams per cubic centimetre. And the density of water is approximately 1.0 grams per cubic centimetre. That's approximately the density of seawater. It will be slightly more dense because it's got salt in it. And so you can see that 0.9 divided by 1 is 0.9. And that is V divided by VT, which means that the volume that is underwater divided by the total volume is 0.9. In other words, 90% of the iceberg is underwater. And so whenever you see an iceberg, you know that despite the massive amount of ice that seems to be above the surface, lurking below the surface is another 90% of the volume of the iceberg. The final question I want to deal with is that it appears to be the case that objects only float if their density is less than the density of the fluid that they are floating in. And that begs the question, how then can a ship float? Because a ship is made out of iron or steel, and that is much heavier, much more dense than seawater. And the answer, of course, is that it is not a massive chunk of iron or steel. What you have is an iron or steel shell that floats in the water. But inside the ship is largely air, so that in fact the combined density of the shell, which is of course much denser than water, but the largely air-filled inside is such that the total combined density of the ship and the air that is contained within it is less than the water, and that's why it floats. Will vary as you go up in the atmosphere. It becomes less dense. And secondly, G itself will vary over the height of the atmosphere. So this is a very rough equation for atmospheric pressure. But when I was at school, the atmospheric pressure on the surface of the Earth was said to be approximately 14 pounds per square inch. These days, of course, we use SI units, and that is the equivalent of 10 to the 5th pascals, which is the same as newtons per metre squared. If pressure is force over area, then force is measured in newtons, area is measured in metres squared, so newtons per metre squared is a measure of pressure, but we actually use pascals. So this pressure is the pressure which results from air having a height h. The same pressure for mass of air. Well, mass can be deduced if you know what the density is. Density is mass divided by volume, and so mass is density times volume. So mass is density, rho, of air, times the volume of air, times G, divided by A. But what is the volume of this cylinder? Well, the volume of the cylinder is simply the area times the height. So AH. And so the pressure is equal to rho times AH, which is the volume, times G divided by A. And the A's cancel, and that gives you rho HG. So the pressure of this cylinder of air as it lands on the Earth is equal to the density of air, rho, times h, the height of the atmosphere, times g. Now this, I have to say, is only an approximation for two reasons. Firstly, the density of the air. Hello, today we're continuing in our A-level physics revision series looking at fluid dynamics and leading up to Archimedes' principle. There's probably going to be more in this video than some of you will need at A-level, but I hope it will give you a good background. In a fluid, the pressure varies with depth, and all the points at the same height in a fluid have the same pressure. So if this is a fluid, then the pressure will increase as the depth increases, but all points at the same depth or the same height will have the same pressure. Let's first consider atmospheric pressure. Pressure is defined as the force divided by the area over which that force is applied. So let's consider the surface of the Earth, and the atmosphere goes up to a certain point, and we'll say that the height of the atmosphere is h. And what we're going to do is to consider a cylinder of the atmosphere where the cross-sectional area here is A, and the height of the cylinder is obviously the height of the atmosphere, h. And we can say that the pressure, which is a result of all the air bearing down on the surface of the Earth, the pressure at, as it were, the surface of the Earth, is equal to, the pressure is equal to the force divided by the area. The force is the weight of air. Remember, there's a difference between weight and mass. Weight is mass times acceleration, which in the case of the Earth's atmosphere will be g for gravity. So the pressure is the mass of the air in this cylinder times g divided by the cross-sectional area A. But what is the water instead of air would result in h equaling 32 feet. And that's for water, H2O. And for mercury, that pressure would result from only 76 centimetres of mercury would give you this pressure. Let's now calculate the pressure underwater. So here is a fluid. It could be any fluid, but we'll call it water for the time being. We know that on the surface of the water, atmospheric pressure, we'll call that PA, is applying. But what about a point here, underwater? Well, once again, I'm going to draw a cylinder. And once again, we can say that the pressure of the water, forget for the moment atmospheric pressure, but the pressure of water on this point here, the pressure of the water is equal, once again, force over area.